Alrighty. Well, hello from Portland, Oregon. My name is John Stoltz. I work at Linaro for the Linaro Consumer Group, and this is my talk on why now is the time to move from Ion to DMA BUF Heaps. So just backing up so everyone's on the same page, what is a DMA BUF? So DMA BUF is a file descriptor, basically kind of a handle that's connected to an abstract buffer, which can easily be passed and shared between userland, the kernel, and devices. It basically allows the buffer to be mapped for DMA by the device, it can be mapped for access by the kernel, and also mapped into userland. So this is a very useful abstraction for sharing buffers between multiple devices and avoiding copies, which is critical for performance. Now I'm going to go through a example pipeline, but there's a bunch of characters involved here, so I'm kind of stretching the material design icon set as far as it can go, so apologies. We have a camera sensor, an image processor, a neural net accelerator, a display compositor, a GPU, a JPEG generator, and the display panel. Now here's the example pipeline. We have the camera sensor that basically will capture an image and write it into the screen buffer we have at the top right. That buffer is kind of, unprocessed raw capture. And so the image processor, we can then pass that buffer to. We'll do some analysis on the buffer, figure out things like white balance, sharpening, brightness, that sort of thing, and create some metadata. That metadata and the buffer can be passed then to the JPEG generator, which will basically scan through the image, create a JPEG, which can then be written out to disk. At the same time that's going on, we can also have the neural net engine looking at the image, trying to find faces and eyes. That information can be fed back into the camera subsystem for things like focusing for the next frame. But we can also use it to have the GPU draw some rectangles onto the UI overlay. Now, which we see here in this red buffer. Now, both the red buffer and the green buffer are passed to the display compositor. The display compositor can also take in some of the metadata from the image processor to figure out that white balance and brightness, et cetera, and apply those changes as it does its compositing. And the net result was basically this blue buffer we see on the screen on the display. Now it's fairly complicated, but it gets a little more complex because we have these constraints to deal with. Now, not all devices can always access all types of memory. For example, some devices can only access physically contiguous pages. Some devices can only DMA to the first 4 gigs of memory. So it's critical that we allocate buffers in locations where all the devices that are going to use a buffer can access. And in addition to this, there's also performance constraints that we have to think about. So for example, every time we map a buffer to a non-coherent device, it's important that we flush or invalidate the CPU cache because we don't want the buffer to get corrupted. That said, if a buffer isn't touched very frequently by the CPU or at all, doing all of these cache operations can be costly. And so it's beneficial to be able to set a buffer as uncacheable if we're just going to be sharing it amongst devices. That said, if the CPU is going to touch the buffer frequently, it's very critical to have the cache enabled for the buffer. So it's really an issue of kind of depending on the set of devices that are going to be used, as well as kind of the path, whether or not the CPU is going to be involved. We really have to kind of put some thought into how we allocate these buffers. So in the example, basically the green buffer was shared with all of the devices here I have circled in green. Now, if say the JPEG engine or the JPEG generator at the very end there, if it has the constraint that it can only access physically contiguous pages, that means that we need to make sure that the buffer that the camera is writing into is in physically contiguous memory. Similarly, if the neural net engine is only able to access the first 4 gigs of memory, we need to make sure that that buffer is both physically contiguous and in the first 4 gigs of memory. Additionally, since the CPU isn't touching this buffer anywhere in this path, it might be beneficial if we have non-coherent devices to set this buffer as uncacheable. Now, for the red buffer, we're only dealing with the GPU and the display compositor. So these may not have the same types of constraints. So they may be able to handle the full address space and handle scatter-gather lists. So we could just allocate just regular system pages. And if the devices are coherent with the CPU cache, there's no real benefit to setting it as uncacheable. So really this kind of shows that depending on kind of the path and how the buffers are going to be used, we need to put some thought into where we're allocating it. Now, DMA BUF Heaps, and really Ion before it, were designed to kind of solve this problem. Basically, they provide a userland interface so that userland can allocate DMA buffs of certain types of memory. And in that way, it's able to allocate memory that satisfies the constraints of whatever pipeline it's dealing with. Now, some might wonder why doesn't the kernel just kind of do this for us? But the issue there is that the kernel doesn't really know where a buffer might go. Userland is the one that's directing what the path is between the various devices that a buffer will take. And so this becomes basically a policy decision. And in Android, this kind of policy is done by the gralloc library. And it basically provides basically a static mapping basically for a given pipeline or usage, what memory type should be used on this device. Now, I know people kind of cringe a little bit that, how do you create a generic solution this way that works on all sorts of devices? But this isn't very different from FSTab. We have a lot of generic distros that work on all sorts of devices that all have, different disk and partition layouts. And so we just need kind of a little file that provides this simple mapping of, this partition goes to this mount point, and that's how it's solved. And so this is very similar in that way. Now, the DMA BUF Heaps framework, it really is a fairly thin layer. It just provides a consistent way for exposing those heaps to userland and allowing userland to allocate these DMA buffs. The heap drivers that utilize this infrastructure are just simple DMA BUF exporters. So it's fairly simple, straightforward. Now, DMA BUF Heaps is very much descended from Ion and influenced by it, but there are some key differences to keep in mind. With Ion, we had the dev Ion device that you'd open, and then basically with the allocation ioctl specify a heap ID to tell it kind of what heap you wanted to allocate memory from. With DMA BUF Heaps, we have per device or per heap character devices. So you can basically reference the heaps by file name. This is beneficial because it allows us to enumerate the heaps very simply. You can just look at the directory. And then also it allows for finer grained permissions so that different heaps can have different access permissions. Another difference from Ion is that we do not support any sort of heap private flags. With Ion, some of the heap flags were able to have different meanings depending on which heaps you were using them with. And so this was just poorly specified and not something that we could really push upstream. And so in the DMA BUF heap allocation ioctl, we do have some reserved flag fields that we may extend in the future, but we want to make sure that any flags we add to the interface are well specified and also generic enough to apply to most, if not all, heaps. An additional difference is that with DMA BUF Heaps, you have full control over your DMA BUF exporter, whereas with Ion, there was a lot of mid-layer logic that would handle that for you. The benefit here is that with Ion, there's a lot of cases where vendors, if they had a kind of quirky heap, some extra functionality that was needed, they'd end up hacking up the common code for that. And that would cause, the net result was that basically multiple heaps from different vendors couldn't really coexist with the same kernel. This was addressed at the very end with the Android 11.5.4 kernel, the last version of Ion. But we've just kind of taken that approach from the start with DMA BUF Heaps. The downside to this, however, is that you may have to maintain a little more logic because we don't have kind of a lot of this mid-layer code. We are open to creating kind of shareable helper logic, but we want to see kind of more heaps upstream before we figure out what components are make sense to share. And really the most important difference between DMA BUF and DMA BUF Heaps and Ion is that DMA BUF Heaps are supported in Android 12.5.10 and newer kernels. Ion has been removed from the staging directory in the 5.11 kernel, and in the Android 12.5.10 kernel, it's been disabled for the GKI kernel. So just looking really quickly at the DMA BUF kernel interface, it's pretty straightforward. There's to get a list of heaps, you can do simple ls on the DMA heap directory. You can open one of those character devices for read and then call this allocation ioctl with the argument structure listed here. Again, an example of that over on the right, allocating basically 1 meg from the system heap and calling the ioctl and then basically returning the DMA buff that comes back. It's all fairly straightforward, but a little low level. If you want something nicer, Google has implemented the libDMA BUF helper library, which basically wraps this allocation ioctl, but I think also more importantly, provides some backward compatibility with Ion. Here's kind of a really brief class description there. And then here's kind of example usage. You instantiate your allocator and then call allocate on it with passing it the heap name and the size that you want to allocate. And that'll provide a DMA buff result. Because doing the dir stats to get the directory listing can be a little fussy, there's also a helper for getting the list of available heaps wrapped as well there. Now, I think what the most important component of this library is this ion backward compatibility support. There's a method called map name to ion heap, which basically allows us to pair a heap name to an ion heap ID and flags tuple. Now, it's a little more complex because there are multiple versions of ion. We had an ABI break at 4.12, and so we have to support both the legacy ion and the modern ion. So basically, this argument's a little more complicated. You have to say, okay, so for the example here, we say map name to ion heap for system, and we pass the ion system name and the ion flag cached, and then we also pass the ion heap type to system and ion flag cache for the legacy ion interface. But the benefit of doing this, you do this once, and then anytime you call alloc on system, it'll do the right thing regardless of which kind of kernel you're on. So if you're on a DMA BUF heap system, it'll open the DMA heap system device and allocate from that. Otherwise, it will allocate from ion, either the legacy or modern. So it's a real nice wrapper there. All right, so if you have an ion heap that you are planning on converting, a couple key items to keep in mind. The big issue is since we don't have any heap flags, you can't multiplex different types of memory out of the same heap. So we need to have one heap per type. Now you can have one driver that exposes multiple heaps. And so you can just export different heap names and be able to do that. But it's really critical that for each variant of memory that you want to expose, you have a unique heap name. Additionally, because we don't have that ion mid-layer logic, you may need to incorporate some of that into your heap driver. Basically this can often just be pulling the ion code into your heap driver itself, or, basically looking at the system or CMA heaps that are already upstream as a guide. And then finally, when naming your heap, I'm asking everyone, please, for any vendor heaps, please use a vendor prefix. So have a vendor heap name as the heap name. So for example, if Linaro had some amazing magic heap, we could call it the Linaro magic heap while it was out of tree. Once we do push something upstream, we can drop that vendor prefix. But what the idea with this is basically we want to avoid having a whole bunch of vendors having out of tree, chunk heaps or something like that, that all are named the same. And then when something does go upstream that's called a chunk heap, there's no way to discern between whether the user space wanted the old legacy vendor version or the upstream version. So as long as there's a vendor prefix, we're able to discern that, and that would save some pain hopefully in the future. Now, there may be some edge cases. I know some folks really, really, really want private heap flags, and they just can't do without them. If that's the case, maybe DMA BUF heaps isn't the right thing for that solution. You don't have to use it. You can always, in your own driver, if you have a DMA BUF exporter, you can always create your own character device and your own ioctl interface that provides whatever arguments you need. Obviously we would like to be able to support as much as we can, but we also have to make sure that the things that we support upstream make sense for the upstream kernel. So we, do reach out to me if there's anything that you think that would be beneficial to extend the interface with. But for now, this is where we are. Now, as for the upstream status, we know with ion, there's been the ion ABI breaks have been painful. And so going through yet another ABI change basically is again painful, but we do want to do this to have an upstream solution so we don't have to go through this again. The status right now is we've completed upstreaming the core framework and the interface upstream. Both the system and CMA heaps have landed. And then also we've added some recent optimizations to the mainline kernel. We still have a handful of patches in Android Common and some work in progress. The shareable page pool and deferred free helpers, those basically provide performance parity between the DMA BUF heap system heap as well as the ion system heap. And that work is in progress. As we submitted upstream, there's been some desire to kind of unify the page pool that we wanted to upstream with other existing page pools in the DRM subsystem. And so we're working on that at the moment. Also, Hrija and Kalesh and Surin at Google have been working on statistics and accounting efforts for DMA buffs. Some of these are moving forward and heading upstream. Others are a little kind of held up on some changes that have been proposed by Daniel Vetter and others to basically support GPU memory accounting in C groups. And so we're trying to figure out how, you know, the DMA buff accounting would fit in with that C group accounting. Additionally, there's been a couple of passes at trying to expose multiple CMA heaps to userland. The one problem with this is we actually don't have any upstream devices that could use this. And so we need to make sure that we have upstream users for any support we try to push upstream. And so if you have a device that would benefit from being able to export multiple CMA heaps to user space via the DMA BUF Heaps interface, please reach out and let me know. I would love to get that enabled. Next is the uncached system and CMA heaps. This one's a little more complicated. Basically, these are heaps that provide really nice performance benefits on some boards. We do have open source Gralloc implementations that make use of it, but right now, the boards that utilize this that would really show the most benefits are using proprietary graphics. And the upstream maintainers have kind of pushed for making sure that we're showing benefit to open graphics and Mesa implementations, and I'll talk a little bit more on that later. I actually skipped one. So heaps is modules. So this is a collection of symbol exports. And the maintainers, in this case, basically wanted to make sure that we aren't enabling just out-of-tree vendor drivers. And so as we start seeing more heaps kind of go upstream, I think it'll be easier to add those exports. And then finally, the in-kernel allocation accessors. This one I'm actually skeptical about. I think it kind of goes against the philosophy of the DMA BUF Heaps solution. But some vendors really needed it in order to make the transition from Ion, so we kind of added that to the Android Common tree to help facilitate the transition. I think we'll be working with those vendors to try to figure out kind of what alternative solutions could be used instead and try to figure out a better solution there. Now, as I mentioned, kind of there's been these pain points with upstreaming. We have, basically, we need to make sure that anything we push upstream, we have upstream users for. We don't want to be just adding helper code that only out-of-tree code uses. And so this is just an important thing. Also, another complexity is that, while the DRM subsystem and the Linux graphics subsystems have long had the requirement that any interface that gets added needs to make sure that it has open source users in user space. And this basically is just to make sure that we're not adding interfaces for proprietary blob drivers. And while with things like this uncached system heap and CMA heap, we do have open source Gralloc implementations, since these still are on boards that use proprietary graphic blobs. We need to find a way to show the benefit of adding these heaps to open implementations or devices that use open implementations. And so I'm going to talk about that a little bit more in the next slide. So strategy for trying to deal with this, my approach is, at least for trying to make sure we have upstream users, is I'm going to pester and nag vendors as much as I can. To try to get those board support submitted upstream and any heap drivers as well. We'll try to kind of dig through vendor trees to try to motivate that and help it along where we can. I know some folks see this as naive and vendors will do vendor things and keep their stuff out of tree. But I'm, a bit of a naive optimist, so I'll just kind of keep on pushing on that. But at a kind of more, deeper level, I think that it's important that we find a way to pull the vendors into the community. These are, folks who are, maybe if they're more product focused or working on stacks that include proprietary graphics, they are still, domain experts that are working on Linux. And I think that, our community would be better to be able to pull them within. And so I want to find ways to kind of keep on engaging, even if we can't engage on everything, but at least on some parts. It's still important that we keep the rules and that we keep only supporting upstream open source solutions. But I think there's ways that we can still collaborate. And And then finally, for this ways to demonstrate benefit for these new heaps with Open Graphics and Mesa devices, this is a little more difficult because it is a bit of a chicken and egg issue. With Mesa focusing mostly on just GPU and display, the allocation methods that it has don't really expect very complicated constraints. It can handle some situations, but not as many. And so just kind of by definition, devices that are supported by Mesa don't really have very complicated constraints. And so we need to find some way to show benefit. And so one of the things I'm thinking about is trying to find ways to kind of look at a more holistic view, not just the GPU display, but also pulling in kind of the V4L2 camera, video, and codec support, and figuring out kind of as those get integrated, we might run into more complicated situations where this would be beneficial. And so following that, basically, we're working on trying to get the V4L2 support in AOSP, working on the Dragon Board 845, which has both open graphics as well as open codec support, and try to see if there's ways that we can utilize the DMA BUF heaps to help kind of that allocation logic and smooth it out. So that is it for me. I will try to take some questions now. If you have any questions, feel free to email me, and I would be happy to try to answer and discuss with you. But while we have, I guess, a remaining couple of minutes, I'll try to answer some of the questions here. So we've got one. So the users of DMA buffs in user space, you couldn't have a buffer heap that, say, for example, could direct where the kernel block cache might live. I'm not sure I totally understand this question. I guess owners might be a better term is the clarification there. So the users of DMA buff are in user space, but DMA buffs can also be used in the kernel by drivers. So it's kind of something that's really flexible and able to be shared, from both sides, as well as a method for kind of doing device DMA, kernel access, as well as user space access. As far as owners, the owner of the DMA buff, since the buffer is somewhat abstract, the DMA buff exporter is the one that basically kind of controls it. And so in the case of DMA buff heaps, the heaps are the DMA buff exporter. And so they basically handle things like the cache synchronization operations and the mapping operations for that buffer. But as far as the owner of it, it's similar to a file descriptor. It has a file descriptor lifetime. So, it's one of those things where once all of them are closed, the buffers are freed. Hopefully that answered the question. I'm not sure. Anything else? Got maybe about 2 minutes left. Try to scan through the chat list here. So there's a clarification that in the last question, the use case is limited to memory sharing between a VM and a service VM, instead of the service VM seeing all of the other VM's address space. So that's an interesting one. I know there has been some stewing on how we might be able to use DMA buffs to pass buffers across VM domains, and so basically as a virtualization concept. I'm not sure where we are at the moment for that. I think right now it still is a in kernel structure. So I don't think we have a way to send it through the hypervisor at this point. But I do know folks are looking at that. There's another question here on does DMA buff have a mechanism for sending a buffer to another OS? And so at this point, I don't believe so, but it's something that I think folks are looking at. All righty, so we're down to less than a minute. I'll see if there's anything else that pops up here. But otherwise, thanks so much for joining and listening, and I hope everybody's doing well. And can't wait till we can all finally get together and have these things in person. All righty, thanks so much.